Day guys. Okay, so in this video I want to talk about 3.1, mainly the definition of momentum, the definition of impulse, and then we'll be looking at a particular graph, which is the force time graph. Right, so let's go into the first one, which is the definition for momentum. All right, so momentum is defined to be the product of mass and velocity. So generally momentum, we use the symbol of P. Okay, and then a mass we use m, and then multiplied by v. So from our previous chapter, note that velocity is a vector, so and mass is a scalar. So a scalar times a vector, what you will get, the product of it, is a vector. So momentum is a vector quantity. Okay, so if we change this momentum, right, the change in momentum, we can find another quantity, which is what we call impulse. Okay, so we define impulse, J, by the change in momentum. Okay, so we can use the definition as before, P equals to mv, to find that, okay, it is the change in any of these two quantity, either mass or velocity. However, in most cases, we do not change the mass, we change the velocity. So then we have J is equals to m, right? And then the change in velocity. As I've said before, whenever you see delta, right, you can expand it into two different situations, which is final state of velocity and the initial minus the initial. Okay, so I would like to borrow an idea from chapter 4, which is the second law, the second Newton's law of motion, which is that force is the rate of change of momentum. Okay, we can expand this, of course, we can rearrange this to get the P equals to F times dt. Okay, of course we can simplify this for our case, which is delta P equals to F dt, or delta T, sorry. I'm gonna cut that off. Delta P equals to F delta T. Okay, now we take this and use the definition of impulse, which is J equals to delta P, which is then equals to F delta T. Okay, so we have defined momentum, we have defined impulse, and we have related impulse to force. Now we are in the position to look at the force time graph. Okay, so let's look at that. So when we talk about graph, there's always two things that we talk about: its gradient and its area under the graph. Let me just remind you again that impulse is defined to be F, force, times delta T. Now, if we're talking about gradient, right, in this ft graph, what we will have is F over T, right? Or if we take some interval of T, then it's going to be F over delta T, right? So at this point, the gradient does not look like the equation for impulse. So does the gradient, right, the gradient of the ft graph represent impulse? It does not. Okay, I'm just gonna let's change colors, let's use red. It does not represent impulse. If we look at the area under the graph, and let's use green, the area under the graph, right? I'm gonna use A, right? Area under the graph. It is going to be F times the interval of T, right? So does that look like J or impulse? Yes, it does. It does look like the equation. It matches with the equation for impulse. Then we say the area under the graph represents impulse. The area under the ft graph represents impulse. Okay, so we have covered the definition of momentum, right, which is mv. We have covered the definition of impulse, which is the change in momentum. We have related the impulse to force, as we can see in this equation up top here. And then we have used this relation to figure out, right, that impulse is equivalent to the area under the FT graph. Alright, so that is what we have covered in this video. In the next video, I'll be talking about conservation of momentum. See you in the next video. Thank you.